So this is section 9.5. And this is from the book. From the book, this is the last thing we're going to talk about from section 9. We have something after spring break that we'll talk about that's not from the book. We're going to talk about limits. So this, and we'll work with a binomial theorem today and tomorrow. So the binomial theorem has to do with multiplying out, finding powers of binomials. So let's remember what a binomial is. Anybody remember what we mean by a binomial? Bi means what? Two. So binomial is just a polynomial with two terms. So an example would be x plus 3. X plus 3 is a binomial. Another one would be 2x plus y. So either of those are binomials, just a polynomial with two terms. And the binomial theorem, we're looking to get binomials raised to a power. So we're looking at binomials, things like x plus y to the n power. And we want to figure out what that looks like if we raise this binomial to certain powers. So what we're going to do, and what mathematicians did in the past, was just start raising binomials to powers and see if we can come up with a pattern. Jackson, would you do me a favor? Would you just twist those blinds open just a little bit? My eyesight's not good enough to see my notes in that. So we're looking at raising this binomial to different powers. So let's do this a few times, and we won't actually have to multiply them out. I've already done it, so we don't have to do it. But we'll see if we can figure out, see a pattern develop. So let's look at x plus y to the 0 power. Anything to the 0 power is just 1. X plus y squared. X plus y squared is, or I'm sorry, the first power. Let's do the first power. I skipped 1. X plus y to the first is just x plus y. X plus y squared is x squared plus 2xy plus y squared. X plus y to the third equals x to the third plus 3x squared y plus 3xy squared plus y to the third. Let's look at a couple more. X plus y to the fourth equals x to the fourth plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the fourth. And we'll do one more, x plus y to the fifth. That equals x to the fifth plus 5x to the fourth y plus 10x to the third y squared plus 10x squared y to the third plus 5xy to the fourth, and our last one, finally, plus y to the fifth. get to that in just a minute. Yes, Cedric. Well, what we could notice that the exponents on each term are different. So this is x squared y. This is xy squared. So we can't group them together because the exponents are different. So what mathematicians did when they did this is they noticed that a pattern was developing. So if we look at this x plus y to the 0 has one term. X plus y to the first has two terms. X plus y squared has 3 terms, 4 terms, 5 terms, 6 terms. So it has one more term than the exponent. We notice that as we go from one term to the next, the powers of x, the powers on x decrease, the powers on y increase. The power on x goes third, squared, first, 0 power. Powers on y go 0 power, 1, 2, 3. And that continues in a pattern this way. Also notice that our coefficients are symmetrical. Here we have 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So our coefficients are symmetrical. So part of what mathematicians do is try to figure out how do I come up with a formula? How can I write out that pattern? How can I figure out that pattern? Now what we're looking at today is these coefficients on the x's on these terms are called the binomial coefficients. So the binomial coefficients come up in a lot of different contexts. That's one reason why they're important. And the pattern that mathematicians noticed is called the binomial theorem. And the binomial theorem is a formula that tells us how we can figure out this pattern. So I wanted to show the pattern first. We're going to write the binomial theorem next, and then we'll talk about what the parts of the binomial theorem mean. And we're going to relate that to what we've been talking about with sequences and sums. So first off, we notice that there's a pattern. We want to figure out how that pattern works. So the binomial theorem. Again, the binomial theorem tells us how this pattern works. And we'll talk about what these parts mean. Some of this might be a little new. We'll talk about what each part means kind of separately. The binomial theorem says x plus y to the n power for any power is the sum. So this is relating it back to what we've been talking about. From r equals 0 to n. N is our exponent of, and this is, we can say NCR. And we'll talk about this symbol in just a second. X to the n minus r, y to the n. So this formula tells us how the pattern for raising a binomial to a power works. Now this symbol NCR, We can also write this as, you'll also see it written with brackets. And what it means is n factorial over r factorial times n minus r factorial.
Is that n over r?
Yes, and that's how we read that, n over r. When we see it in brackets, it's the same as this symbol, and it means, and this is how it's defined, n factorial over r factorial times n minus r factorial. And the way you might have seen this before, this NCR, that's the number of combinations of n things taken r at a time. So if you did any probability at all, if you studied probability in the past, this is how we figure out the number of combinations of n things taken r at a time. And this is how we calculate it. So this sum gives us our pattern for the binomial theorem. And we're going to work with the parts kind of separately to develop them. And we're going to work with the binomial theorem today and tomorrow. So the coefficients, the binomial coefficients come from this formula. The numbers that we came up with back here, the 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, that comes from calculating this with our binomial. And this pattern, the n minus r, x to the n minus r, y to the n, gives us our pattern with the exponents. So this formula gives us our pattern. So let's look at some calculations using our binomial coefficients, using this NCR or n over r, calculating some of these. So let's say we want to calculate 10C5. The other way that you'll hear people talk about this is 10 take 5. We're going to calculate 10 take 5. 10 things taken 5 at a time. So I'm just going to write the equivalent notation. And this equals 10 factorial over 5 factorial times 10 minus 5 factorial. Yeah, Cedric.
Will we get to use the factorial, but to not make factorial?
Yes, and your calculator will actually, I think your calculators will do this calculation. I think we'll look for it in just a second. But I want to show the longhand way to do this, just so you understand, because this looks complicated. It's really not that complicated. So this is 10 factorial over 5 factorial. 10 minus 5 is 5 factorial. I can rewrite this as 10 times 9 times 8 times 7 times 6 times 5 factorial over 5 factorial times 5 factorial. These cancel, so I get 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times 1. And 3 times 2 is 6, right? So those cancel. Because I cancel all the rest that come after 6. 4 goes into 8 twice. 5 goes into 10 twice. So I get that this is 2 times 9 times 2 times 7. And I calculate that out and I get 252. So if you do some cancellations, these things work out pretty easily. Now let's see if we can figure out where this is. I can't remember off the top of my head where this is on your calculator. So let me go there and we'll get that.
It's under math.
Is it in the math menu? So let's see. We'll clear this. In math, we go over here to probability. And go down here to 3. And let's see, how do we...
You have to type in a number first.
You type in the number,
The first number, and then you do NCR,
and then,
and then you type in the last number.
so
So it's like
10 NCR. So for the problem that we just did, we would type in 10. We would do 10, and then we go to math, and then we go over to probability. What? Need to, oh, okay. So we do math.
No, you don't. 10 first.
Oh, right, 10 first, thank you. 10, then we do math. There we go. Go over to probability. And we're going down to 3. And then we do 5. And then hit enter. So your calculator will do those combinations for you.
So we can check that.
Right.
Try it.
All right, so let's go back and let's look at a couple of other of these. Because there's actually, we saw in our binomial coefficients that we had a pattern. We actually have a pattern, and the pattern comes from the way this works. So let's look at a couple more of these. So 8C2 or 8(2), and that, the way we would calculate that is 8 factorial over 2 factorial times 6 factorial. And if you calculate that out, you get 28. You can do that any way that we want. If we did 12C4 or 12 over 4, 12 choose 4, 12 factorial over 4 factorial times 12 minus 4 factorial is 8 factorial. If you calculate that out, you get 495. And if we did 12C8 or 12 over 8, 12 choose 8, 12 factorial over 8 factorial times 4 factorial, what do you see between these two? Aren't they the same?
No.
We have a 4 factorial and 8 factorial in the denominator, 4 factorial and 8 factorial in the denominator. These are the same. In general, and that's where, yeah, Travis. So you're saying, can you do 4C12?
Yeah.
No. The number you choose from has to be bigger. So the first number has to be bigger, because we can't choose 12 things out of 4 possibilities. So that wouldn't work. All right, so our pattern in our binomial coefficients comes from the pattern in these combinations. And the general rule is, if we have NCR, that is the same as n choose n minus r. So we had 12 choose 4. That's the same as 12 choose 8. Well, 12 minus 8 is 4. That's where this comes from. And our definition, we're going to define n choose n is always the same as n choose 0 is 1. So if we're picking all of the things at a time, our number of possibilities is 1. If we're picking none of them, Our possibilities is 1. So this is part of what gives us our pattern in the binomial theorem. It's because our combinations work out this way. Questions on how to calculate these coefficients? So these come from our factorial, and our pattern in part comes from the pattern in this. Or this relates to the pattern in our binomial coefficients. Now let's go back to this pattern again. And if we write just the coefficients of just the binomial coefficients in rows and columns like this, we get a special arrangement called Pascal's Triangle. And it can be an easy way to get some of our binomial coefficients if our exponent is kind of low. And Pascal's Triangle is a really cool thing. There are a lot of secrets, a lot of mysteries in Pascal's Triangle. So we're going to write the pattern just for the coefficients. And I'm going to write them in a triangle. And I'll do another row. All right, so you guys see the pattern. What are we doing to generate this triangle? Adding the two things above, and that gives us what's directly below. So we start with 1. These two are 1, so we always have 1s on the outside. 1 and 1 make 2, so we're adding those two 1s to get the 2. I add the 1 and 2 and I get 3 here, and I'm just adding the 2 above to get the next one. If we look back at our pattern for our binomial coefficients that we talked about on the very first page, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. It matches up with Pascal's triangle. So we can use Pascal's triangle to get our binomial coefficients. The numbers in Pascal's triangle are the binomial coefficients. So this would be, the first row would be for n equals 0, n equals 1. We call this the 0 row. N equals 1, n equals 2, n equals 3, n equals 4, etc. And this gives us the coefficients of x plus y to the 0, x plus y to the first, x plus y squared, etc. So these are the coefficients of these binomial expansions. Pascal's triangle, there are a lot of things in Pascal's triangle. If you add the numbers in each row, the sum of all the numbers is 2 to the n, where n is this number here. We can find the Fibonacci sequence in Pascal's triangle. You can do lots of different things with Pascal's triangle and get a lot of different, very interesting math out of Pascal's triangle. It was known as far back as Pascal, they call it Pascal's triangle, but they have writings in ancient China where the ancient Chinese had written out Pascal's triangle. They realized this pattern. They understood that it was significant. So it's been around for a long, long time. But so this way, you don't have to memorize. You don't have to memorize all those coefficients for some of the lower numbers, for the lower exponents, and you don't have to calculate those NCR NCR numbers. If you know Pascal's triangle, you can construct it. Yeah.
Where's Fibonacci's numbers in this?
Let's see. The way you go kind of upwards on a diagonal. So this is 1. You go 1, 1 is 2. 1, 2, 1 is 3. 1, 3, 2 gives you the 5. You go kind of upwards on a diagonal, and you get Fibonacci sequence. All right. So let's stick with me, guys. Pascal's triangle gives you a way to figure out your binomial coefficients fairly easily for low numbers, low exponents, without having to go through all the calculations. It gives you your pattern. Well, let's look at a few examples of calculating some binomial expansions. So this is part of what you're going to have to do on your homework. So let's figure out, we want to figure out the expansion 2x plus 3 to the 5th power. We want to expand that out. Now to do this by hand, you'd have to multiply, you'd have to do a lot of multiplication, a lot of simplification. But the binomial theorem tells us this is the sum from r equals 0 to 5 of 5CR x to the 5 minus r y to the r. And here are x and our y. Instead of x and y, we have 2x and 3. So I'm going to substitute those in. This is 2x to the 5 minus r. And my second term is, in my binomial, is 3. And to find this expansion, all I need to do is write out each term of this sum. So if I write this out, this is going to equal, starting off with r equals 0, 5c0 times 2x to the 5 minus 0. We're starting with r equals 0. 2x to the 5th, 3 to the 0. That's my first term. Plus, now we do the term for r equals 1. 5c1 times 2x times 5 minus r equals 1. 5 minus 1 is 4. 3 to the 1st power. Plus, now we're going to do the term for r equals 2. 5c2. 2x to the 5 minus 2 is 3. 3 squared. Plus now r equals 4. Three, thank you. R equals 3. So 5c3, 2x to the 5 minus 3 is 2. 3 to the 3rd. Plus, now we're at r equals 4. So we get 5c4. 2x to the 5 minus 4 is 1. 3 to the 4th. And finally, r equals 5. 5c5 times 2x to the 5 minus 5 is 0. 3 to the 5th. And I can calculate all of these out. We know how to calculate these 5c0, 5c1, 5c2. We do 2x to the 5th power. So we're going to raise 2 to the 5th and multiply it by this number. 2 to the 4th, multiply it by this number. 2 to the 3rd, multiply it by this number. So when we write this all out, when we calculate this all out, I'm not going to go through all the calculations. We get 32 32x to the 5th plus 240x to the fourth plus 720 x to the fifth plus 1080 x squared. Wait, this should be x to the third, sorry. X to the third, 1080x squared plus 810 x plus 243. So if we multiply all these numbers out, raise all of these to our exponents, this is our expansion. Any questions on that?
Yeah, is there a shortcut to that?
No.
Then how is that faster than actually pulling it out?
Because when we FOIL, we end up with, you have to, basically you do 2 parentheses at a time, and then you have to combine, you have to simplify, combine, add.
For that, you have to, I think that would be just as difficult. I mean, time-wise, and then confusing-wise, like, that's just, when you FOIL it out, it's pretty straightforward with that.
If you, now think about what would happen if you had something like something like 1.8x plus 3.7. Raise that to the 7th power. So that would be more difficult, I think, to FOIL than calculating these. Right, right. What the main point of this is to see that there is a pattern to the binomial expansions. The pattern has to do with a summation. The pattern has to do with this factorial notation, and there's some symmetry, and there are some shortcuts than just cranking through foiling these problems. So let me do one more quick example, and then we're going to work with this some more tomorrow. We do have homework. We want to find, in this example, we want to find the coefficient of x to the 8th in the expansion of x squared plus 2 to the 12th. All right, so in this example, we know that x squared plus 2 to the 12th equals a sum. R equals 0 to 12 of 12CR x to the 12 minus R 2 to the R. And we want x to the 8th. So 12 x squared, sorry, this should be x squared to the 12 minus R. This is just our binomial expansion. So x squared to the 12 minus R has to equal x to the 8th. Yes?
Are you going to give us, like, these formulas? Because there's a lot of them for you here.
Yes, I will give you formulas. So in this example, we know that x, because we're looking for the coefficient on x to the 8th. This is my formula for the binomial expansion. So x squared to the 12 minus r has to equal x to the 8th. So 12 minus r has to equal what in order to give me x to the 8th? If I raise an exponent to a power, 12 minus r has to equal 4. So R has to equal, what does R have to equal? 8. So R has to equal 8. So to find the coefficient on x to the 8th, I plug in, my coefficient is going to be 12c8. X squared to the 12 minus 8 is 4 times 2 to the r is 8. That's going to be my coefficient. That's how I figure out my coefficient. And it turns out when I calculate all this out, I get 1, 2, 6, 7, 2, 0, x to the 8th. So this is my coefficient. All right, homework. Page 659, 1 through 41. Every other odd. We'll work with the binomial expansion some more tomorrow. So some of this doesn't make sense today. We'll work on it some more tomorrow. We're not learning anything new tomorrow.
Homework from last night.
Okay.